Hello and welcome. Today I'm going to talk about measuring frequency with an old analog oscilloscopes. As you know, an oscilloscope doesn't only measure voltage, it can also be used to measure the frequency of an AC waveform. And the first thing I'm going to do is go ahead and try to get a clear and stable display with my oscilloscope here. So I'm going to go ahead and adjust the trace to get it on the zero baseline, and I'm going to go ahead and adjust the horizontal position, center it, so right about there. And I've got my connections made are as follows. The leads coming from the oscilloscope are basically just hooked up to leads coming from the audio generator, which is basically plus to plus and ground to ground. This here is my leader audio generator. I've got it preset up to about 700 Hertz. I'm going to go ahead and turn it on. Now we'll get back to our display. Now, in order for me to measure frequency, like I said, I got to get a clear and stable display, a readable display. Basically, you want to get it so one complete cycle, the waveform, fills out the screen. And this is, evidently you can see here, this is all too scrunched up. So I'm going to go ahead and adjust my horizontal time base. It's on right now. See, it's on 1 millisecond per second. I'm going to go ahead and adjust that. That's still kind of scrunched up. I think that'll do it right there. That's 0.2 milliseconds per division. And also you need to adjust your, basically your vertical step here. And that would be like off, ready off the screen, which is way too high. And this will be way too low, so I'm going to go ahead and do it like that. Now, in basically, I always like to assume that the beginning point of the cycle is the point where the signal crosses basically the baseline. But in this case, I'm going to go ahead and just go ahead and take the top of the positive side of the AC waveform, where basically it starts to where it ends. Now what I got to do is count the horizontal divisions from the beginning of one cycle basically to the start of the next. Okay, we'll go ahead and do the counting now. So I'm going to go ahead and adjust this horizontal position again, and that's right in the middle there at the very peak. I'm going to take that as the start. I'm going to count over 1, 2, 3, 4, 5, 6, 7. Looks like 7.2. So what I have to do is multiply this by the time base in order to get the time period. I'm going to go ahead and do the math now. So now we're going to go ahead and do the math. Remember, we measured 7.2 horizontal divisions, and we had the time base, we had the horizontal sweep set for 2 milliseconds per division. So doing the math, we take the 7.2, which was our measurement, and then we times that by 0.002, which is 2 milliseconds. As you might remember, a millisecond is a thousandth of a second. So we get 0.00144. That equals 1.44 milliseconds. Now, next, in order to get frequency, we use this formula here, which is the frequency equals 1 over the time period. So we take the 1, we divided that by the 0.00144. That gives us 694 hertz. So I'm going to go ahead and do some more measurements. This one at a different frequency. I've got my audio generator hooked up to put out 15,000 hertz. Again, like I said, we want to go ahead and get a stable and clear display. So I'm going to go ahead and adjust my horizontal time base now. This is still the 0.2 millisecond time base. That's the time base I used for the last measurement for the 700 hertz. You can see 0.2. So now I'm going to get and start adjusting. That's 0.1, which is still too scrunched up. And that's now I'm into microseconds. Now microseconds, of course, a microsecond is a millionth of a second. This is 50 microseconds. This is 20 microseconds. This is 10 microseconds. This is 5 microseconds. I obviously can't use 5 because part of the waveform, part of the cycle is completely off the screen. It still has to be on the screen in order for me to make the measurements. I'm going to go ahead and use this right here. This is, let me focus in on this. That is 10 microseconds. Now I'm going to go ahead and do my counting again. I'm going to go ahead and adjust my vertical. I'm at 2 volts per division. I can't use 1 volt per division because, as you see, the display is going to go completely off the screen. And using 5 volts per division, it's going to be, well, kind of low. You want to get it to take as much space on the screen as possible, but where you can still do an accurate measurement. So I got it back up here to 2 volts per, basically 2 volts per division. Now I'm going to go ahead and start doing the counting. I'm going to adjust my horizontal again, and I've got it right in the middle here, where on the second division you see where it ends, right. And I'm going to start there. That's basically the high point of the cycle here, of the waveform. So that's 1, 2, 3, 4, 5, 6, 7. I would say that is about 6.8. I would say about actually 6.9. So I'm going to go ahead and do the math now. So now here's the math for this measurement we just did. We're going to take the 6.9 horizontal divisions that we measured, and we're going to multiply that by our time base of 10 microseconds per division. So doing the math, that comes out to 0.00069, which is 69 microseconds. Then in order to get the frequency, we're going to take 1 and we're going to divide that by the time period. So that's 1 divided by 0.00069 equals 14,492 hertz. Now that is kind of a, like I said, this is not a 100% accurate way to do things. It's a ballpark figure.